So today we're going to take one of the skills that we've been using for a long time, finding factors and greatest common factors, and we're going to learn how to apply this when we're talking about monomials and polynomials. So remember first that whole numbers that are multiplied to find a product are called factors of that product. So a number is divisible by its factors, of course. You can use the factors of a number to write the number as a product. So, for instance, the number 12 can be factored several ways. So let's look at some examples. Okay, all of these work. If I multiply these out, these all equal 12, but only the last group of factors is a prime factorization. This group at the end is a prime factorization because none of these numbers are able to be divisible by any number other than 1 and itself. So these examples all have composite numbers. These are strictly prime numbers. So we're going to be working on prime factorization. Remember that a prime number has exactly 2 factors, just itself and 1. But the number 1 is not prime because it only has 1 factor. So 1 is not a prime number. So let's start with an example. Find the prime factorization of 80. And remember back in 6th grade or whenever we worked on it, we did these factor trees and we took out a 2 and 2 multiplied by 40. We took 40 and said that was 2 times 20 and 20 was 2 times 10. 10 was 2 times 5. And if you look, we're going to go back and circle all our prime factors. And notice that what we have is 4 2's, or 2 to the 4th, times 5. So these are all now prime factors, and this would be considered the prime factorization of 80. We could have also done this so that it looked like kind of upside down long division. 2, 40 to 22. You can do it whichever way makes the most sense. Here are all of my prime factors. So again, I would have 2 to the 4th times 5. Do a couple of these just for practice. Pause your video, come on back. Okay, so factors that are shared by 2 or more numbers are called common factors. The greatest of these is called the greatest common factor, or GCF. So, greatest common factor. Let's look and see how we're going to find the greatest common factor. One way to do it would be to just list out all the factors of each of these numbers. I want the greatest common factor of 45 and 60, so I'll start. That's 1 times 45, and then I've got 3 times 15, and then I've got 5 and 9. So I've got all these factors for 45. My 60 is 1 and 60. 2. You can do this however it makes the most sense for you. I'm just trying to quickly go through and find all my factors. I've got 4, 15, 6, and 10. Okay, so if I look down my list, I can see that the greatest common factor here is 15. Okay? So another way that I think might be a little bit easier is just to go ahead and write the prime factorization of each number. Well, 24 is going to be 2 times 3 times 2 times 2, and 36 is going to be 3 times 2 times 3 times 2. Well, what do I have in common here? I've got 1, 2 here, I've got another 2 here, a 3, a 3, a 2, and a 2. So my greatest common factor is going to be the product of those 3 common factors, or 12. So 12 is my greatest common factor. So you pause the slide for a second, pause the video for a second, and try this one out. Okay, what we all been waiting for, we're going to apply this method to monomials. All right, so we are going to write the prime factorization of each of the coefficients. Then we're going to write all the powers and the variables, and then we're going to find the product of the common factors. So we're going to start this with an example, finding the greatest common factor of 18g squared and 27g cubed. So I've got my 18g squared. 18 is going to be 3 times 3 times 2. 27 is going to be 3 times 3 times 3. Then my g squared is really just g times g. And my g cubed is g times g times g. So I've got 3 as a common factor, 3 as a common factor. I've got 1g and a second g, so I've got 3 times g times g as my common factors of these two monomials. So that's 9g squared is my greatest common factor of these two monomials. Let's look at another example real quick. I've got 3a squared and 5b to the fourth. Well, what would I have that would be, how would I factor this? I can't, so I don't have anything to take out of my coefficient. And then notice my variables are completely different too, so there's nothing I can factor out of here that is common to both of these. But I'm going to give you an opportunity to try it out on some that may or may not have common factors. Pause your video and check back in a second and see if you've got this. Another one of our skills, the distributive property, to help us in factoring. So remember, the distributive property basically just says that here my A would have been distributed to the B and the C, which gave me the AB plus AB multiplied together plus AC multiplied together. Okay, so we're going to kind of do that backwards to help us with factoring. So the distributive property is going to help us factor out the common factors and leave us with a factored term. Okay, so notice here I'm going to find my greatest common factor. Well, I've got nothing in the coefficients, but I do have in the first term a common factor of x. So I've got a greatest common factor of x, which was x, and notice I still have a 5x squared left up there, and I need to subtract what's left as my 7. So I've pulled out my greatest common factor, and I could go back and prove to you that I've done this correctly by multiplying my x times my 5x squared, which would give me 5x cubed, and my x times my negative 7, which would give me negative 7x. So in fact, this is factored for the greatest common factor. Okay, so I'm going to factor both of these, looking for the greatest common factor. Notice this time I have a coefficient that actually can be factored as well. Here I've got a 2 times x, so I've got a 2 that's common to both as well as an x, so I've got a greatest common factor of 2x, which means that I can pull that 2x out, multiply that by the remaining x, and subtract 2. And in fact, if I went back and distributed, I would have gotten 2, or I would get 2x squared minus 4x, which is where I started. So I have factored out by the greatest common factor correctly. So let's look at another example. Here I've got a coefficient that is absolutely going to factor. I've got 2 times 2 times 2 times 5a's. And I've got a negative 4, but that's going to be 2 times 2, and I've got 2a's here. And then my 20 is going to be 2 times 2 times 5 with just 1a. Well, common to all three, I've got 2 2's and I've got at least one A that's common to all three, so I've got an A here. So the greatest common factor of these three monomials is 4A. Well, what's left? I've got 2A to the fourth. I'm subtracting an A, and then I'm adding a 5. And I can check this for myself. This is 8A to the fifth minus 4A squared plus 20A. Okay, so this one I'm saying is not fully factored. Why is that? Well, of course, it's because I've got an x that's common to both of them. I can pull that x out, so now I've got a 3x times 5 minus 7. So this would have been 15x minus 21x, and this is still 15x minus 21x. 10n squared plus 3, can we factor that? Nope, we can't take anything out of either of these monomials that is common to both. So this one's fully factored. Okay, here's your opportunity to try to factor completely. Pause your video, try this out, and see what you get. Notice here that I have no common factor between these three, so there is nothing I can do to factor at this point. Okay, so I know all you love real-world examples, so let's go. I've got a cafeteria that has 18 chocolate milk cartons and 24 regular milk cartons, and the staff wants to arrange the cartons so that they're the same number of cartons in each row, but not mix the chocolate and the regular milk. So I want to know how many rows there are going to be of chocolate and regular milk if they put the greatest possible number of cartons in each row. So in order to do that, I'm going to have to find the greatest common factor of 18 and 24 so that I know how many could be in each row. 18 is going to be So I found my greatest common factor of 6 by fully factoring these two numbers. I know now that there can be 6 of each carton in each row. If I've got 18 chocolate milk cartons and 6 are going to be in each row, then obviously I'm going to have 3 rows of chocolate. And then I've got 6 in each row, 24 or 4 rows of regular milk. So I have a total number of 7 rows, which answers the question, how many rows will there be if I put the greatest possible number of cartons in each row? So here are some problems for you to work on. Please bring these in your notes to be checked in class tomorrow.